That postdoc was the program's Singularities paper, which has been submitted, and that's the content of today's talk. Currently, I'm a part-time employee at Timaeus. I love having philosophical or even practical conversations about existential threat as much as the next guy, but in my soul, I'm a math nerd, so my main approach to AI safety and all the other things that we've been talking about in this conference so far has been the beautiful mathematics that I have been lucky to study behind SLT. I'm also a part-time musician and performance artist. I only mention this because there is a huge range of people that are very interesting at this conference, and I think that sometimes it's helpful to wave a few flags. I am working on projects outside of my work in Timaeus. So I've got various mathematical musicology projects. I'm working with a master's in music student on various different things. This is stuff not relevant to the talk, but if anybody has interest in these types of things, please do talk to me about it. And as far as the performance stuff goes, I've done these fun little mathematics drumming performances. That's what you see on the left there. And on the right, that was a collaboration that I did with with some of the world's best GoldenEye 007 speedrunners. That was a lot of fun. All right, so let's get to talking about mathematics. Algorithmic structure and geometric structure, or structural Bayesianism, as this talk has been pitched several times. So we could be interested in expanding the proper domain of logic or computation to include that which emerges inside large language machines other than ourselves. And one way of doing this is to embed proofs or programs viewed in the same light via the Curry-Howard correspondence into machine learning or singular learning theory. If we were to create such an embedding, then this embedding really should be a homomorphism. I'm using the phrase homomorphism here somewhat as an analogy. What I really mean is that it should be structure preserving. So what we want to do is look at something that is computational and has algorithmic structure, which we can look at and observe, and then embed that into some kind of geometric setting where we can see reflections of that algorithmic structure inside the geometric structure. Okay? And today's talk is basically just an example of one of these homomorphisms, somewhat of a proof of concept, and indeed it's the main takeaway from the paper with the same title as the talk. On the right, you can see some examples of the geometry that you get when you analyze the algorithmic structure geometrically according to the tools that I'm about to present for you. And these pictures are totally awesome. There's a lot that you can say about them. The picture credit is to Billy Snickers. He's talking next, and he'll be running through some of those diagrams by way of example. Very cool stuff. Why believe in this in the first place? So I've stolen this motivation from a talk that Dan gave a little bit earlier. It's worth saying out loud that all of the work I'm talking about today has been done in collaboration with Daniel Murphy. Okay, so there's this quote. If you're a scientist or if you're an engineer and you're trying to understand effective causality, then you really want to understand the perturbations of every constituent component of that thing that you're trying to study. That's somewhat wrapped up inside this quote. And the simple question that we began with is, what would it mean to perturb the computational process of a Turing machine? What would that mean? A very natural first suggestion would be to instigate probability somehow. So if I were to perturb a Turing machine, maybe that means to put some kind of probability into its inputs. This can be done using standard propagation of uncertainty through a Turing machine. However, we believe that this is insufficient, as you end up studying the probabilistic extension of the function which is induced by the Turing machine. And that's really not what we mean by propagating error or uncertainty through a Turing machine. We really want the error or the uncertainty to be propagated through the computational process itself. So what would that mean? The way that we thought about this was by running simulations of Turing machines on a fixed choice of universal Turing machine, and then considering perturbations of that computational process. So we fixed a very particular universal Turing machine. It's a so-called staged pseudo-universal Turing machine. And this is really important to a lot of the work that Dan and I have done in this paper, and also to the examples that Billy is going to talk about inside the next talk. So I'm going to spend a little bit of time right now explaining the actual computational process of this particular universal Turing machine that we take. First and foremost, we work with a fixed alphabet and set of states. So sigma is just some size n set, and q is some size m set, where sigma is the tape alphabet and q is the set of states of the Turing machines that we're trying to simulate on this universal Turing machine. Now, what this means is that a Turing machine is completely determined by its transition function, which can now just be given as a sequence like this. So when you say sigma 1 prime, q1 prime, d1, that corresponds to the first output that you get from the transition function of a Turing machine that you're trying to simulate. So when you see sequences like these, I want you to be thinking about them as the code for a Turing machine, which is going to be taken by this universal Turing machine. The universal Turing machine has got 4 tapes on it: a description tape, a staging tape, a state tape, and a working tape. The description tape is where the code for the Turing machine that you're simulating goes. Okay? So that sequence that I've got up here with the green arrows pointing to it just goes straight onto the description tape. The staging tape just only makes use of 3 squares, and it's just got X's on it to begin with. I'm going to come back to the staging tape. The state tape only uses a single square, and it just stores the information of the state of the Turing machine that we're simulating. And then down on the bottom is the working tape. This is how the universal Turing machine simulates the actual computational process on the tape of the machine that we're simulating. Okay, so what is the actual operation of this universal Turing machine? Well, initially all of the heads are on the far left, except for the staging tape, which is in the middle, but don't worry about that for now. Pay attention to the description tape. If the head of that tape is right on the left, then it means that we're looking at the first output of the first symbol inside the transition function of the Turing machine that we're simulating. And then we're going to compare that symbol to the symbol that is underneath the head of the working tape. And that's in order to see whether we get a match or not, to know in the next step if we should then compare the state, and then if we find a match, then we're going to write down the correct output of the transition function onto the staging tape as we continue moving along the description tape. Okay? So to summarize, the Turing machine is going to go along the description tape and just search until it finds a match, and when it does, it just puts that information into the staging tape to then update the working tape at the next phase of the computation of the universal Turing machine. Okay, so after the first pass, the staging tape is ideally occupied because the updated symbol, the updated state, and the updated direction have been written onto it. And then there are a few and a fixed number of steps that are dedicated to updating the state and the working tape. And then the description tape simply moves the head back to the very start, and we clear the staging tape back to the X's, and then we're ready to simulate the next step of this Turing machine. Okay. Any questions about that? So this naturally gives us a space of Turing machine codes. It's this space W code, and it's just the product over all sigma and q, where lowercase sigma is ranging over capital sigma, our alphabet tape, sorry, our alphabet language, our tape alphabet, there we go, and q is ranging over all of the states. Okay, so an element of this space is just one of those sequences which I'm using to describe the code of Turing machines. And then what we want to do is fix one of the squares on the description tape of the universal Turing machine and consider a perturbation of that square. So what do I mean by a perturbation? Well, at this point we introduce the probability simplex. So just as an arbitrary definition, if z is a set, then you can define delta z to be the functions from z into the closed interval from 0 to 1. Essentially these entries sum to 1. This is just probability distributions over the set z. The reason why I introduce this is so that we can define a concept of a noisy Turing machine, which is given by a function of this form, which is very similar to the form of a regular Turing machine, but now our outputs are able to be distributions over the alphabet states and also the directions. Okay? And you can see how W code naturally embeds inside this space W. And one point of remark about the space W is that it is a smooth manifold with corners, right? So now that we have a smooth space, we would hope to install it with non-trivial topology, which will allow us to study the local neighborhoods of elements inside W code.
Question?
Yeah.
So just to review naively,
Yeah.
sigma and Q are properties of the universal Turing machine. They're not separate for each Turing machine you're encoding.
You're talking about lowercase sigma and Q, or
Uppercase sigma and Q.
yeah. So it's somewhat a property of the universal Turing machine. It's the choice of alphabet and the choice of states which our universal Turing machine are able to simulate machines that use that alphabet instead of states for. So to put it simply, fix a set sigma, which is your alphabet, and then fix a set of states, Q, and then we're going to consider a universal Turing machine which is able to simulate Turing machines with that alphabet and set of states.
Don't Turing machines have to be arbitrarily big and you fix it?
Yeah, absolutely. So in that sense, this is not a universal Turing machine.
Okay.
It's a staged pseudo-universal Turing machine. We're also going to only run it for a fixed number of steps, blah, blah, blah. Was there another question?
Maybe intuitively, the program stays the same, but the compiler is noisy, or the interpreter is
Interesting.
noisy?
If we're talking about the program as being the code that we put onto the Turing machine, it's not really the same. I mean, we are actually going to change one of the symbols to a probability distribution over that symbol, right? Indeed, this is fuzzy or noisy computation, or, you know, however you want to think about it. But it can make a difference. That's kind of the point. You want to look at all of the local perturbations and see what makes a difference and what doesn't. And then we want to describe those differences geometrically. Make sense? Yeah. Yeah.
So, I guess as long as, so there's going to be a continuum of elements in the simplex, but I guess there will be some dense subset that are computable real numbers, and then you could always have some probabilistic Turing machine that simulates this behavior, right? But you may have to add some more states and the stream of random bits, and then you, right? So ultimately, so you're basically expanding this from the space of deterministic Turing machines into some built-in set of probabilistic Turing machines.
Yeah, 100% we are taking our set of Turing machines, which is some discrete set, and then we're going to embed it into a continuous space. It sounded to me like the first part of your question was asking about computability of those probability distributions, in case I take some...
Well, I guess I'm just saying that there will be some dense set within this larger space that are the computable probability distributions. Right, so in a way, this is like you're just expanding to a set of Turing machines, probabilistic Turing machines, and kind of taking the closure.
Sure.
Yeah.
Okay, yeah, we can think about it like that. We are taking a very particular type of probabilistic Turing machine, which is a non-standard one, and that's an important part of the theory. I'll talk about that as well. We didn't think about computable probability distributions. Did you want to say something, Dan? Or?
I think that's not quite correct. It's the way we're going to execute those other points is not going to...
That's okay. That's what I'm curious about. What's the difference?
It's not dense. It's not that there's like a set of dense, computable, like this. When you're interpolating sort of between some hypercube, which is interpolating the deterministic programs are the corners of this hypercube. Rather than what you're suggesting is that there's like a dense set of computable.
What he was saying makes sense, but the answer to your questions complicated.
Okay, sure. We can talk about stuff.
Cool. So maybe this is actually going to clarify things. Computing with perturbations, what does it look like? So I think I've made the point, but I just really wanted this image to kind of be in mind. These are the four tapes of the pseudo-universal Turing machine. And the top one is the description tape, so you've got zeros, ones, describing your Turing machine. And then we're going to fix one of the squares and introduce a perturbation. So where you see 1 minus epsilon 0 plus epsilon 1, think about that as the correct symbol there is a 0 with a small probability of having a read error when you read a 1 instead. But you sample from that distribution. That's why I've put this 1 here. It's not as though the entire distribution flows through the computation of the pseudo UTM. Instead, we sample and then move whatever we get. So say we did make an error and have that one, we move that into the staging tape, which then gets propagated all the way through the computation. Okay? Cool. So since we're not just taking standard probabilistic Turing machines, we want it to be principled in the way that we construct the propagation of error through our universal Turing machine. And the way that we did that was we made use of linear logic. To this particular audience, it's probably worth saying out loud, you don't need to know linear logic to understand our paper, okay? And it was important to us that we wrote it in such a way that hopefully that was transparent. I'm not sure if we succeeded. But you don't need linear logic in order to understand it. But it was a language that we used in order to construct the precise way in which probability, or the precise way in which error flows through the computational process. And then we distilled all of the linear logic out at a certain point. You can just think about it as a particular probabilistic Turing machine, but you need to kind of just accept it on the nose if you don't take the background of linear logic into account. So this is the only slide where I'm going to talk about linear logic. What is it? It's a formal language, it's a system of logic, and nowadays computer scientists are familiar with the Curry-Howard correspondence, which allows us to view certain constructive logics as systems of computation. Linear logic is no exception. And linear logic is cool because it comes with a natural notion of derivative. Yes, I'm telling you that you can take the derivative of your algorithms, which is not so surprising nowadays, but when I was 10 years younger and I was meeting Dan for the first time, that was super cool for me. So, to achieve the smooth relaxation of the computation of a Turing machine, we actually encoded Turing machines running for a fixed number of time steps t into linear logic. And then we looked at the naturally occurring naive probabilistic extensions of the algorithms inside linear logic, the way that those things perform on the proofs encoding Turing machine specifically. So as I said, linear logic has a natural notion of derivative inside its syntax, and so this also allows us to analyze the derivatives of the proofs, in particular the proofs encoding the computation of the staged pseudo-universal Turing machine. And we claim these derivatives are interesting. So instead, what you should think about is this. Now, I apologize for putting this slide on the screen, but you know what? I don't apologize. I'm proud of myself for putting this slide on the screen. I wanted to explain it, and I wanted to have some chance of the people at the back being able to see it. So, no title, no words. What are we looking at? Okay, this is the way that error propagates through our staged pseudo-universal Turing machine, just concretely written down as a graphical model. So every single node here is a random variable, and all of the arrows give you the dependencies on those random variables on what precedes it. To help you with reading this diagram, it mostly goes from 0 up. There are some diagonals, but you never go down or sideways or anything like that. Over on the far right, you'll see this counter from 0 up to 10n plus 6. Capital N here is the number of blocks of 5 here. So what's n? N here is determined by how many symbols and states you have inside your inside the machine that you're simulating. Okay, but these time steps are just the true time steps of the universal Turing machine, and 10n plus 6 such steps gives you one simulated step of the Turing machine. Okay, so we're looking at a single step of the Turing machine that we're simulating. Is this symbol visible? There's a theta here. Okay, that theta is where we're introducing the error. So this is the 1 minus epsilon 0 plus epsilon 1 that we saw on one of the previous slides. And then what you want to think about is everything that precedes this theta. So everything for which there is a directed path from theta to that random variable has a dependency on that error that you introduce. Okay? So this gives us a way of thinking about the probabilistic computation of the UTM. And yeah, when Dan, myself, Billy, etc. Thinking about these computations, this is truly the diagram that we have inside our heads, okay? Yeah, question.
Okay, so now I guess maybe am I prepared to ask the question? So if theta is a computable number,
Yeah.
then it seems to me that I could introduce some more states where I run a computation of theta and I flip a bunch of coins, right? And I get more and more precise intervals for theta. And once I know that my coin flips kind of land, I sample from the uniform distribution. If my coin flips land below theta, right? Then I take the transition, the one transition. If they land above theta, then I take the other transition. So I end up writing something on a different thing on my tape, depending on what I take a different transition depending on what I see. Right? So I still don't understand how this is not. I mean, at least for the computable perturbations, I still don't understand how this is not a probabilistic Turing machine.
So it's
Dan,
because
do you want to grab this?
so the question was like, why isn't this just executing a probabilistic Turing machine? So the reason is, if you think about the model of the UTM executing this code, it's quite exotic in the following way, where every time it's going to read from a square at some later step, it's going to sample as many times from that original uncertainty as it needs to in order to reconstruct every step in the chain leading to that square. So it's like some wildly growing number of samples where you sample like many times all the way back to the very beginning, which is, so you could probably simulate that as a probabilistic Turing machine in some way, but this is not the usual way. So I'm not disagreeing that you could not reach the same output probability. I'm not saying it's uncomputable or something, but it's not the usual way you would parameterize a probabilistic Turing machine.
Yeah, I guess, okay, I have to think about this a little bit, but I'm still not sure I see how it's different, because at the end of the
It seems
day,
like it has
when you get to
different
the
memory
output-
constraints.
What?
It seems like it has different memory growth profile as it runs.
But I'm not sure it does. Like when you get to the final output, then you just propagate all the way back to the
I
beginning.
think that might be true, but it's sort of, okay, so what?
So this then, it's not so much I'm just saying, is this?
Yeah, so the claim is not this is some exotic, interesting new class
Yeah.
of computation. The claim is that this is a way of constructing a geometry which is interesting. So if you do it that's maybe also a related or maybe the same way of coming across the same geometry. So the claim is not that this is like something that's completely outside of probabilistic geometry.
There was another question here. Did you? No. Thanks. Oh, yeah.
Oh, yeah, I just had, so would it be a decent summary to say that the sort of probabilistic model here is you sort of flip, a bit of your source code basically, or the machine description at random, and then you keep it flipped until it flips back basically for the rest of the computation?
I wouldn't say so. You're replacing a bit in the description tape with a distribution.
Yeah.
And then every single step of the universal Turing machine thereafter that at any point in its history can be traced back to that distribution, you're going to resample. So you definitely don't fix it. This is important. You don't take one sample once and for all, or even for one simulated step and then do it again. It's really not like that. So if you're really deep inside your computation of your pseudo UTM, there's just going to be a ton of dependencies back on that square from ages ago. And that's what happens.
Okay, you resample every random node in your past history every time.
So every time you come...
I see. Yeah.
I saw another hand, yeah.
So equivalently, could you just kind of represent every dependent node itself as a distribution rather than actually sampling it and kind of stay in distribution space, do you ever have to draw samples?
No, you can just.
Yeah, you can do that for sure.
Can you repeat the question?
So the question is, do you actually need to do the resampling, or can you just basically consider the distribution induced on all of these random variables? Which certainly you can. Are you coming to grab the mic?
I'm just going to sit in the shade somewhere. I don't have it.
The reason why we do this is because we want to think about this as an ongoing computation, right? But so on the next slide, I'm going to talk about this function, which takes in an element of, say, some string, and then a noisy Turing machine, which is one of these codes in W, and then it outputs the distribution on the state at the very end. This is just a simplifying assumption to say, okay, this is crazy. What if we just fix one of these states and then look at all of its dependencies after, say, 2 simulated time steps?
I think, Will, you didn't describe what the columns are. Maybe we could.
Oh, that's a very good point. So each column is, each group of columns is corresponding to one of the tapes on the pseudo-universal Turing machine. So this first column, which has a lot of blank entries on it, is the description tape, okay? I haven't put in every single symbol because it's deterministic and you don't need to. But this theta being the thing that we're considering as a perturbation, that's happening on one of the squares on the description tape, okay? So this column corresponds to the description tape. The next 3 columns correspond to the staging tape. The next 2h plus 1 columns, so from here over to there, correspond to the working tape, and we need to track the movements of the head on the working tape as well. And the way that we do that is by keeping the head position as the central element. So we append symbols on either on the left and the right, depending on whether we move to the left or the right. So when you see a left or right movement, consider that as moving the entire tape instead of moving the head. And then over here, the second column from the right, they're the states of the pseudo-universal Turing machine itself, which I didn't actually introduce, so that's probably a bit of a confusing column. And the last one is just a time step counter for the pseudo-UTM. So if you take one of these random variables, say this Q here, then you're looking at all of the dependencies throughout the computation of the pseudo-UTM that lead to this particular random variable. And that's how we were thinking about this delta step t function. So there are a few simplifying assumptions here. You can look at the entire output of the step function, but that's a bit crazy. So we just look at the state. You can think about that as a Turing machine that accepts or rejects a string, for example. Okay, and then we define this posterior to be this delta step function, and we define this function h, which is some expected value, some sum of squares.
Not the posterior, it's just the model.
Yeah, this model, sorry, and then this function here. And these are the geometric objects that we associate to a Turing machine. Okay, do I have that on the next slide? Yeah, I've got it here. So programs as singularities, programs here are Turing machines, and the singularities here are these pairs. So associated to a Turing machine M is the function germ M, comma H, where bracket M means the code of M, and H is this function here.
Say what a classical solution is.
A classical solution is when the true distribution is described by a Turing machine, so the function y here is computable, and then M is a Turing machine whose induced function agrees with that of the Turing machine corresponding to the true distribution. So that would not be probabilistic. Oh, I guess it could be. Sorry, delete that last sentence. Okay, so we described these we describe the geometry of this using the language of inference functions, which we define inside the paper. So these are just the partial derivatives of this model P that I had on the previous slide. Okay, and you can actually get some interesting behavior by just looking at the first derivatives. So when we are looking at an indexing corresponding to the standard basis vector, then we just write G sub I, where I is the position inside that standard basis vector, the position of the one, and then we write that instead of G sub I bold. Cool, so these functions are one of the central objects inside our paper as well. We've got this monster 90-page paper. This is hopefully saying, pay attention to these things if you're trying to read it. And this is one of the first lemmas that we had, where we can understand the partial derivatives of h in terms of expected values of these influence functions. Okay, so I've put the full definition on the slide, but just think about C, I, J as a constant. It's something that doesn't depend on the Turing machine itself, or it doesn't depend on the influence functions, and then you can see that the right-hand side is really determined by these functions Gi, Gj. Cool. So now we want to relate this to algorithmic structure, and, oh, sorry, there's a question here. Yeah.
So W is the working tape string, or?
W is your description, so just...
It's a bit string?
Yes, it's a bit string.
How do you take derivatives with respect to...
Ah.
W is your local coordinates.
Yeah, the W1 up to the WD are the local coordinates of the space capital W, which is your manifold with corners, where points on it are these probabilistic Turing machines. These noisy Turing machines, I should be calling them. Right? And so you're taking a derivative of a function defined on a smooth manifold with corners. You do that by defining local coordinates and then taking normal partial derivatives.
So W's are coordinates of these probabilistic Turing machines.
Yes. So one coordinate Wi corresponds to a pair of bits inside your description tape where you take the difference of them. And you think about that as lowering the probability of reading one of those bits and increasing the probability of reading the other bit.
Epsilon was an example
Epsilon?
of, you had epsilon going from simple 0 to simple 1.
Yeah.
So epsilon is one of these directions.
Okay. Very good. If I don't see your hand, please shout out. Will, I've got a question. Okay, so we mostly relied on intuition, but we can give some pretty concrete examples. Robustness to error would be one of them. So now we've kind of got a game that you can start playing, right? You have Turing machines on one hand, and you have these algebraic singularities on the other, and you can just go to town on that. You can say, okay, what feasible structure of the algorithm could I conceive of? And can I chase that through the mathematics and see if I can get some kind of visibility of that inside the function joke? We found a few such examples. One of them was robustness to error. Another one is control flow. So if you have a Turing machine that basically splits the inputs into two different types, and the first thing that the Turing machine does is works out whether you're of type A or type B, and then does process 1 if you're of type A and process 2 if you're of type B, then you can see that computational structure, that algorithmic structure, reflects structure inside the Hessian matrix of this function h, which I defined as part of the function show. And I'll talk about that in a second. Okay, so to really nail down the algorithmic structure, we introduced this notion of error syndromes. And an error syndrome is a simple thing. As I was saying, the computation of this UTM goes back in history and takes a whole ton of samples on your